Welcome to the deep dive. Today, we are taking on a really persistent and honestly a damaging failure in modern education.
Mhm.
We're talking about the way we teach decimal numbers.
Right.
And if you've ever, struggled with fractions or you found yourself just completely lost by place value after the comma, or maybe you still do those weird mental gymnastics when you're calculating a tip, well, this deep dive is definitely for you.
It's for a lot of people, I think.
It is. And we're not looking at, minor tweaks to the curriculum. We are analyzing a proposed structural overhaul, a complete refounding of the whole approach.
Yeah.
And it's based on research that suggests the problem fundamentally isn't with the student, it's with the system itself.
It's such an urgent conversation to have because the stakes here are just incredibly high. The sources we've been looking at, they frame this thing we always hear about, the numeracy crisis, in a very specific way. They argue that this crisis, it's not evidence that students are getting, less intelligent or something. It's the direct result of these deeply flawed pedagogical approaches that actively mask the meaning behind the math.
So it's a crisis that's been manufactured by the method we use to teach.
Exactly. It's manufactured.
And within that whole process, it seems like decimal numbers are singled out as the critical breaking point.
They are.
The sources, they even call this moment an epistemological rupture, which is a heavy term.
It is, but it's accurate.
Think about it, right? Students spend their first few years in this very safe, discrete, countable world of whole numbers. You have 2 oranges, you add 3 more, now you have 5 things. It's concrete.
Simple, 1-to-1.
And then bam. Suddenly they're thrown into this continuous, dense universe of measurement, where things aren't just 1 or 2 or 3. They exist in these fractional relationships.
And if they don't bridge that conceptual chasm, their ability to grasp anything higher algebra, calculus, even, complex financial literacy, it's just fundamentally compromised from that point on.
This isn't just about general frustration in a math class either. Our sources make a really strong case that this specific failure acts as an accelerator for academic inequality.
Right. It's an equity issue. When the method itself is flawed, it disproportionately harms the most vulnerable students. We're talking about students who really rely on structural clarity, on concrete representation, to build any kind of understanding.
Including those who need special educational support.
Absolutely.
And to put a finer point on that, the sources get really specific. They mention, for instance, the French ULS or SEXPA programs. Now, for listeners who aren't familiar with those acronyms, just imagine specialized units. They're dedicated to helping students with significant learning difficulties, things like dyscalculia or other cognitive dysfunctions.
And when even that targeted support system is struggling, it's a huge red flag that the foundation of the teaching material itself is just rotten.
The method itself is putting up barriers that these students are the least equipped to get over.
That's it, exactly.
But the real power of this critique, I think, is in the long tail of the failure. The most damning evidence isn't a bad test score in 3rd grade.
No.
It's the errors that persist, the ones that stick with us right into adulthood, even in people who are successful and otherwise very competent. It's like a neurological trace, proving the concept was just never truly grasped.
And here's where the diagnosis gets really specific and I think really powerful. Think about that one. Absolutely canonical, reproducible mistake. You ask someone to calculate 3.14 plus Bandro 1, and they confidently tell you the answer is 3.15.
I can see that. I can immediately trace the logic, even though I know it's wrong. It's a cognitive shortcut.
And the sources are really blunt about this. They call this specific repeated error the neurological trace of a pedagogy.
Oh.
It is not a random accident. The mistake happens because the student's brain defaults to a rote reflex that was ingrained by the teaching system. It sees the numbers 14 and 1. It treats them like integers. It adds them to get 15.
So the brain is not seeing 14 hundredths added to 10 hundredths.
Not at all. It's just seeing symbols on a page.
It's applying the rules that work perfectly for whole numbers to a decimal operation, where those rules are, well, catastrophically wrong.
Precisely. And what that does is it exposes an educational system that is focused almost exclusively on teaching the manipulation of symbols, the syntax, while completely sidelining the fundamental understanding of quantity and magnitude, which is the semantics.
And when you see that specific systemic error repeating across generations,
It stops being an individual learning difficulty.
right, it becomes a structural failure of the teaching method itself.
Absolutely.
Okay, so that really sets the mission for this deep dive. Our first goal is to scientifically dissect why this traditional algorithm-centric teaching is so flawed, the structural diagnosis.
And then second, we're going to introduce the proposed structural overhaul, this colored rectangles method. And this isn't just, another class shade. The sources we have present this as a complete pedagogical engineering solution. It's designed to be a powerful lever for academic success and, maybe more importantly, for restoring educational equity by offering a clear path for the students who are currently failing because of bad pedagogy.
Let's start with that hard look in the mirror then, the diagnosis. Before we can even talk about a new method, we have to understand exactly what flaws the traditional methods are actively reinforcing. What's the fundamental cognitive bias we're up against?
It is overwhelmingly something called the natural number bias. This is the intellectual root of almost every persistent decimal error you see.
Okay, natural number bias.
So when a student sees a decimal number, let's say 4.75, they don't perceive it as a single quantity, 4 and 75 hundredths. Instead, their brain uses what's called a bipartite view. They see two totally distinct whole numbers that just happen to be separated by a point. They see a 4 and they see a 75.
So the decimal point becomes a wall. It just divides the world into two separate integer universes.
It's a perfect analogy. And the moment that wall goes up in their mind, the student inappropriately applies all the rules that were so successful in the world of integers to this new continuous mathematical space.
Because the brain loves efficiency. It loves consistency.
Of course. If a rule worked for all the numbers before the point, it's just going to try and generalize that rule to all the numbers after the point. It's a logical but flawed leap.
Okay, let's slow this down and really unpack the canonical example that the sources give, because this comparison really highlights how that bias just derails any understanding. The task is simple. Compare 3.15 and 3.8. Which one is bigger?
And this comparison is an absolutely deliberate cognitive trap. It's almost perfectly designed by the traditional pedagogical approach because it showcases two distinct but related paths of erroneous reasoning.
Okay, so it's path one.
Path one is treating the decimal parts as isolated integers.
Meaning?
The student just ignores the place value entirely. They extract the numbers after the decimal point. So they compare the 15 and 3.15 with the 8 and 3.8.
And in the world of integers, 15 is obviously bigger than 8.
Of course. So the student, very logically from their point of view, concludes that 3.15 must be the larger number. And this is just a profound failure to understand that the 8 actually represents 8/10, while the 1 in 3.15 represents only 1/10. The magnitude is completely lost.
They're treating 0.15 as if it's just further along the decimal chain than 0.8.
Exactly. It's a total conceptual disengagement from the idea of fractional value. But path two is often even harder to shake, and that's the length bias.
The length bias, the visual cue that, more digits must mean a bigger number.
It's a visual heuristic that works flawlessly for whole numbers. You compare 99 and 9, the longer number is bigger. Every time.
But with decimals, it fails instantly.
Instantly. The student sees that 3.15 has two digits, a 1 and a 5 after the point, but 3.8 only has 1, the 8. So they deduce that the number with more digits in its decimal part must be quantitatively larger.
That's fascinating because it really just shines a light on the students' confusion over what these numbers actually represent. They completely miss the semantic truth. That 0.8 is 8/10, which is the same as 80 hundredths.
Right.
While 0.15 is only 15 hundredths. The magnitude is just gone. It's lost in this pursuit of visual pattern matching.
That is the absolute core of the failure. The student knows that positional value dictates worth before the decimal point. They get that. But that understanding just completely evaporates the second they cross that separator.
And the natural number bias kicks in.
It causes them to revert to counting discrete units rather than understanding proportional value.
Okay, so that's the cognitive root. Let's move to the second major problem the sources identify, which is, I love this term, pedagogical iatrogenesis.
It's a fantastic term.
Explain it for us.
So as we touched on, iatrogenesis means basically an injury that's caused by the remedy itself. In medicine, it's a side effect of a treatment. Here, the remedy is that ubiquitous traditional column-based algorithm, the one that tells students, when you add or subtract decimals, you just have to align the decimal points.
Okay, but why is that mechanical procedure actually making the underlying conceptual disease worse? I mean, on the surface, it seems so practical.
It is practical, but only in the narrowest, most syntactic sense. It enables purely syntactic success.
Meaning a student can get the right answer without knowing why.
A student can follow the physical instructions, line up the points, bring the point down into the answer, fill in the empty spaces with zeros, and get the right answer without engaging in any semantic understanding at all. They can get 3.24 for 3.14 plus 0.1 without having a clue that they were combining tenths with tenth and hundredths with hundredths.
So the algorithm is basically a sophisticated workaround. It allows success to happen at the same time as this profound conceptual failure. That's a huge problem for actually diagnosing the issue.
It is, because the teacher sees the right answer and moves on. The sources argue that this approach incorrectly reifies the decimal point.
Reifies.
It means to make something abstract more concrete, so they elevate the decimal point from its legitimate, simple role as just a separator.
Like a piece of punctuation.
Exactly. Just a final bit of punctuation between the whole part and the fractional part. They elevate it into this central, almost mystical operator that has to be aligned or brought down into the solution box.
So it turns the decimal point into the main event instead of just the stage curtain.
That's a great way to put it. And by doing that, the method reinforces the idea that decimals are just strings of characters that need to be manipulated spatially in a column. And that leaves the student totally defenseless when they face any problem that requires estimation or checking if an answer is plausible.
Because if your success just depends on lining up the column correctly, you lose any intuitive sense of the quantity.
Exactly. If you calculate 3.14 plus 0.1, you get 3.15, and the teacher only cares that you align the points correctly on the next problem.
The structural error is never fixed.
Never. And that lack of semantic feedback, it just necessitates a radical philosophical departure from this method.
Okay, so that philosophical shift is where the colored rectangles method comes in and starts its work. The core idea seems really simple, almost elegant. It's about subordinating the mathematical operations entirely to the physical magnitude and the intrinsic nature of the quantities you're working with.
Yes, you are dethroning the digit's position in favor of its actual quality.
It's a method that's grounded in embodied cognition, then.
It is. It's about anchoring these very abstract concepts in things that are irrefutable, physical, sensory. It makes the number real again. It forces the student to perceive the value, to handle it, to compare the quantities physically.
And the robustness of this system, it seems to rely on what the sources call the triple sensory congruence. It's not just using one type of manipulative. It's three synergistic anchors that are designed to overwhelm and override those flawed cognitive biases we just talked about.
We should really take some time to appreciate the engineering here. Let's start with anchor 1, mass, where value literally equals weight.
This has to be targeted directly at overriding that visual bias, right? The idea that a bigger digit means a bigger value.
It is. Remember the natural number bias. Visually, a student sees the digit 9 as intrinsically more than the digit 1, and that bias persists even if the 9 is way down in the thousandths place, like in 0.009, and the 1 is in the units place. The written symbol fails them.
So you're saying the physical experience of actually holding the blocks has to counteract that symbol bias.
It has to. If a student tries to compare 0.009 and 1 using these blocks, they would physically hold a pile of 9 tiny little red milliem rectangles in one hand and a single, much larger green unit rectangle in the other. The physical weight, the mass of that single green unit is vastly greater.
So their physical intuition, the feeling of the mass, it overrides the visual bias of the symbols 9 and 1. It's an irrefutable sensoromotor truth.
Exactly. So when they're asked to demonstrate an equivalence, like, say, 10 times 0.1 equals 1, it's not just a fact they have to recite from memory.
It's something they can feel.
It transforms that abstract rule into a material reality. A stack of 10 blue tenth rectangles has to physically balance or have the same weight as a single green unit rectangle. It makes the concept of value conservation palpable.
Okay, so anchor 2 is area. Size is a visual anchor. This one seems to go directly after that insidious length bias we talked about, where students assume 3.15 is bigger than 3.8 because it just looks longer.
And the proportional size of the rectangles is the defense against this bias. If a student is still holding on to that intuition that more digits means a bigger number, the material system forces a visual confrontation.
So walk us through it. Let's say we're comparing 0.09 versus 0.1 using this area concept. What does the student do?
Okay, so the student would take 9 of the small gray hundredth rectangles, and they'd align them side by side in a row. Then they place one of the larger blue tenth rectangles right next to that collection.
And the visual truth is just undeniable.
It's undeniable. The area of that single blue tenth rectangle is substantially greater than the total area occupied by all 9 of the hundredth rectangles put together. And this physically, spatially, invalidates that wrong intuition that 0.09, represented by the 9 little gray pieces, is in any way comparable to or bigger than point 1, represented by the single large blue piece.
It's like an internal immediate feedback mechanism. The math is proven correct right there by the geometry of the manipulative.
And that leads us to the crucial third anchor, which might be the most important of all: color. Color dictates nature before position.
So this strict color, coding green for units, blue for tenths, gray for hundredths, and so on, this is the fundamental didactic variable in the whole method, isn't it?
It is the ultimate cognitive shortcut, and it's used very strategically. It acts as a powerful visual discriminant. What it does is it drastically reduces the cognitive load that's required for positional analysis.
So the student no longer has to analyze complex positional information like, is this the second or the third digit after the point?
They don't. They just identify the quantity's intrinsic nature by its color. This creates these sealed mental categories.
So the command in their head becomes group blues with blues, grays with grays.
Exactly. And that simple instruction instantly restores the semantic understanding that the traditional algorithm completely bypassed. You're not aligning abstract numbers based on some external arbitrary rule. You are physically grouping same-colored, same-natured quantities.
And this restoration of semantic understanding, it paves the way for what the sources dramatically call the epistemological coup,
It's a great phrase.
which is the radical assertion that the decimal point plays no role in the calculation.
And this is the moment of liberation for the student. The goal here is to strip the decimal point of all its unwarranted pedagogical baggage and just restore it to its true, humble function, a simple, final punctuation mark.
So during the actual operations, the adding and subtracting, the student is told to just ignore the decimal point completely.
Ignore it. They are manipulating only the colored, quantifiable chunks of value. The greens, the blues, the grays.
They're calculating based on the nature of the unit, no matter where that point is scribbled on the paper.
Precisely. They focus purely on combining and exchanging these colored quantities. And only once the physical action is complete and they've organized the final material result, let's say they have 4 greens, 1 blue, and 6 grays on the table, only then is the decimal point reintroduced.
That was the very last step.
The last step. To separate the whole number, the greens, from the fractional part, the blues and grays. The operation is about quantity. The decimal point is only about the notation of that quantity. And that separation is revolutionary in demystifying the entire system.
So we've established that the blocks make the numbers real,
Yeah.
but physical manipulators can often fail if they just allow students to mimic motions without any conceptual engagement.
Right. That's a common critique.
And the sources stress that the success of this colored rectangles method, it hinges on an engineering of constraint, or what they call constructive frustration.
Yes.
So the material itself has to block the wrong procedures and force the student to invent the correct mathematical concept out of pure necessity.
This is the absolute genius of the didactic engineering. The material limitations, they act as didactic blocking variables. If the material allowed the student to just retreat to their old habits, like, getting 11/10 and just writing 11 somewhere, the method would fail. The constraints force a conceptual reckoning.
Let's analyze addition first. The idea of regrouping is a technical necessity. What are the key material constraints that are at play here?
There are 2 crucial non-negotiable constraints that really embody the base 10 system. The first one is the max 10 rule. The student only ever has a maximum of 10 rectangles of any given subunit color. So 10 blues, 10 grays, and so on.
Which means if you acquire an 11th one of something, you've broken the rule and you have to perform an exchange.
That is the necessity. But the second constraint is just as tactical, and this actually addresses the critique about the cost of materials. The number of green unit rectangles is deliberately limited, often to just 4.
Wait, only 4 units? Why not 10 or 20? That seems odd.
It's the essential didactic blocking variable. If students had unlimited unit blocks, they could just try to convert everything into big whole numbers.
Okay.
Like if you were adding 1.5 and 2.5, they might try to get 40 tenths and then just exchange them all for 4 units.
And that would let them avoid dealing with the decimal structure.
It lets them sidestep it. Limiting the units forces them to operate within that crucial abstract zone of decimal numbers where the proportional value of the subunits, the tenths and the hundredths, truly matters.
That's a very strategic constraint.
Yeah.
So let's walk through an actual calculation. 0.6 plus 0.5.
Okay. The student starts by laying out 6 blue 10th rectangles and 5 blue 10th rectangles on the table. They physically combine them, and now they have a stack of 11 blue rectangles.
And the moment they have 11 blue rectangles, what happens? The alarm bells go off.
The max 10 rule immediately kicks in. The physical rules of the game, the rules of this material scarcity. They forbid them from having 11 rectangles of the same color. It's a physical impasse. They are stuck.
They have a mathematically correct quantity, which is 1.1, but they have a materially forbidden representation, which is 11 blues. The system has engineered a problem that requires a solution.
And the only material solution available to them that conserves the value is the exchange. They must physically trade 10 of those 11 blue rectangles for one green unit rectangle. The one leftover blue rectangle stays where it is, and the new green unit gets placed in the unit column.
This is really powerful. The abstract, memorized algorithm of carrying the one is just transformed into a concrete, necessary technical solution to a material scarcity problem. They didn't just move a symbol on paper, they proved that the value of those 10 small parts is precisely conserved by exchanging them for one large part.
Regrouping becomes intrinsically linked to the physical conservation of value, not just the rote movement of symbols.
Okay, now for the more challenging side of things, subtraction. The method uses breaking as a form of conflict resolution to demystify borrowing. And this is where most students get completely lost in traditional methods.
Borrowing is mystical in traditional teaching. It's magic. The rectangles method strips away all that mystery by using the material constraint to demonstrate the inherent necessity of the algorithm. Let's use that critical example from the source, 0.3 minus 0.29.
Okay, so the student starts. They lay out 3 blue tenths to represent 0.3.
And they need to perform the subtraction, which means they have to remove 2 blues and 9 grays.
They can successfully remove the 2 blues. That's easy enough. That leaves them with 1 blue rectangle, which is 0.1.
But here comes the conflict. A cognitive and a material impasse arises. They must now remove 9 grays, 9 hundredths, but they have none on the table. The operation is physically, materially impossible. They cannot complete the subtraction.
So they're forced to admit that their current material representation of the number, the 0.3, is inadequate for the operation they need to perform.
Exactly. And the mandatory solution is to break the remaining blue 10th rectangle. This means they must physically exchange that single blue rectangle for 10 gray 100th rectangles. So now they have 10 grays on the table.
So the abstract action of borrowing from the tenths column isn't just a pencil mark. It's the material necessity required to acquire the subunits they need to finish the subtraction.
They've transformed 0.1 into 0.10 in a physical, value-conserving move. Now they can easily remove the 9 grays from the 10 they have available. That leaves them with 1 gray 100th rectangle. The final result is 0.01. The whole process is transparent. Borrowing is completely demystified.
And this leads right into the profound discussion about the organic emergence of zero.
Yes. In traditional methods, the teacher just instructs students to, mechanically add a 0 to 0.3 to make it 0.30. And the explanation is usually it doesn't change the value. It just feels like a trick.
The rectangles method flips this completely.
It does.
So how does zero appear organically?
In that same 0.3 minus 0.29 example, the 0 that converts 0.3 into 0.30 is the written trace of a physical material event. It represents the newfound availability of those 10 hundredths that were created after they physically broke that 10th unit.
So it's the visual record of the value-conserving transformation they had to perform to make the calculation possible.
It teaches the student a crucial, semantically rich concept. That 0.3 and 0.30 are the exact same quantity, but 0.30 is a representation of that quantity that is more suitable for a specific calculation.
So the 0 isn't just a syntactic placeholder you add mechanically.
No, it's the physical acknowledgement of a reality you created through the exchange. And this anchors that abstract notation in material truth, which is just absolutely vital for vulnerable students who struggle with notation that's divorced from reality.
This sounds incredibly powerful for all students, but the sources are really keen to emphasize its structural role as a tool for combating educational inequality. So for students with special educational needs, those with dyscalculia or cognitive limitations, how does this method specifically alleviate that severe cognitive burden that's imposed by traditional abstract math?
The method was structurally engineered from the ground up to be a targeted response to common cognitive dysfunctions. The main goal is to address the limitations of working memory and executive function.
Right, because traditional algorithms just overwhelm the working memory. You're trying to juggle the calculation, the spatial alignment, the borrowing rules, and remembering the numbers all at once.
It's too much. The rectangles method offers 2 primary mechanisms for relief. First is task sequentialization. The operations are systematically decomposed into distinct, manageable steps. First, you manipulate the blocks. Second, you exchange if you need to. Third, you write the final result. The student is allowed to focus intensely on one physical or cognitive action at a time. This chunking drastically lowers the cognitive barrier to entry.
And the second mechanism is memory externalization.
Yes. This is absolutely crucial for students whose working memory is already severely strained. The number itself is physically present, it's stable, it's visible on the table in the form of these colored blocks.
So the student doesn't have to keep 3.14 plus zero point 0.1 memorized internally while they're also trying to manage the complex process of regrouping.
Right. Those mental resources are freed up from just raw memorization, and they can be reallocated entirely to reasoning, to critical thinking, to problem solving.
And that ability to free up cognitive bandwidth, that has to be transformative for students with cognitive challenges.
It is. And this brings us to a feature that might seem counterintuitive at first. It's what the sources call the didactic speed bump. The time that's required for the physical manipulation, the placing of the blocks, the counting, the exchange, it's not seen as an inefficiency. It's seen as a highly strategic feature. The source calls it a Freinmotor.
A frame motor, a motor brake. So the method deliberately applies the brakes to the student's process. Why is slowing them down an advantage?
It's all about inhibiting impulsivity. Struggling students often rely very heavily on quick, reflexive answers, what psychologists call System 1 thinking, because it avoids the effort of deep calculation.
They just want to get an answer on the page.
Exactly. The mandatory procedural slowdown of physical manipulation, it acts as a cognitive dampener. It inhibits that impulsive response, and it forces the activation of controlled analytical reasoning System 2 thinking.
So the requirement to physically interact with the material actually buys the student the necessary cognitive space to think properly.
Precisely. This procedural slowdown becomes paradoxically an accelerator of understanding. It creates the necessary space for students to self-assess their actions and to self-correct based on direct material feedback.
So if they end up with 11 blue rectangles,
The physical system provides immediate, undeniable proof that they've made a mistake. It forces them to build metacognitive autonomy by correcting themselves.
okay, we have to address the elephant in the room when it comes to manipulatives. This method sounds intellectually superior, but scaling material is expensive. And a lot of teachers use money as a concrete manipulative for teaching decimals because it's universally accessible.
Right.
So why does the source material argue so strongly that the colored rectangles model is conceptually superior to, say, using dollars and cents? I want to introduce some critical resistance here on the practical application.
That is a vital question. And the sources anticipate it. They established the rectangles model as a pure base 10 laboratory. And while money is accessible, its conceptual structure is polluted by the social conventions of currency.
Let's break down that comparative failure. If we look at the basis of meaning for the three models, the rote model's meaning is just spatial position. The money model's meaning is based on the social value of currency. But the colored rectangles model's meaning is based purely on physical magnitude, area, and mass. That already feels cleaner.
It is cleaner. But the greatest failing of the money model is in the mechanism of regrouping the very heart of the base 10 system. In the money model, the exchange is irregular. Think about coins. You don't just have dimes and pennies. You have pennies, nickels, dimes, quarters.
Right. So you might exchange 5 nickels for a quarter. That's a 1-to-5 ratio. Or 4 quarters for a dollar, 1-to-4 ratio. 10 dimes is 1-to-10. That irregularity just confuses the fundamental, non-negotiable structure of the base 10 system, where every unit is precisely 10 times greater than the next smaller one.
The money model uses the abstract concept of value, which is socially defined, and it applies an irregular conversion ratio. This completely undermines the mathematical goal. In stark contrast, the colored rectangles model enforces a constrained, pure, base 10 exchange, a strict 1-to-10 ratio at every single level, from the tiniest red piece up to the tens.
So it provides a pristine environment for students to construct a robust, unadulterated understanding of mathematical architecture.
Yes. It uses sensor motor cognition to build a mathematical concept, not a fluctuating social convention.
So while money might be easier for a teacher to get their hands on, it's actually teaching the student irregular conversions, which ultimately conflicts with the very structure of the decimal system we are trying to convey. The intellectual cost of using money outweighs the material cost of engineering the right manipulative.
That is precisely the argument. The use of the money model risks what we would call semiotic pollution. The symbols and their associated actions, like irregular exchange, they contaminate the pure mathematical concept of positional value. The colored rectangles are a clear, strong, semiotic code that dictates the rules, not confuses them.
This method is presented as pedagogical engineering. And just like any great engineering project, it requires a precise blueprint. The sources are absolutely non-negotiable on this point. Its effectiveness is entirely conditional on adhering to a rigorous four-phase progression. If you skip a phase, you're guaranteed to regress right back to mechanical abstract learning.
This structured progression is what prevents the blocks from becoming just another classroom toy. It ensures that the conceptual understanding built through physical manipulation is properly internalized and then abstracted.
So phase one is material appropriation. What's the objective here?
The objective is purely non-formal. There's no calculation introduced. The student has to build an intuitive sense of magnitude, they have to establish the base 10 equivalences, and they have to actively dismantle that natural number bias, all through physical play.
And what does that look like in a classroom?
It looks like constant, repetitive exchange games. Give me one green unit and I'll give you 10 blues. Or comparison games. We have two piles here, one is 0.8, the other is 0.15. Without counting the digits, who has the physically larger pile? The student has to handle the blocks, feel the mass difference, see the area difference, and just internalize the physical truth that 10 small parts always equal one large part of the next magnitude up.
And this phase could take weeks, but it's the foundation.
It's the non-negotiable foundation.
So once that physical intuition is really established, then we move to phase two. Pure manipulated calculation.
And here, the objective is validation. The student has to prove to themselves that the solution emerges logically from the material itself, not from some external rule that the teacher gave them. This builds a profound confidence in their own innate mathematical reasoning.
And the emphasis here is on the material reality over any kind of written notation.
Exactly. The student solves complex operations, additions, and subtractions that involve regrouping and breaking, using only the physical material. They physically lay out 0.3, they perform the break, they remove 0.29, and the only written trace they produce at the end of all that is just the final answer, 0.01.
So they have to perform and explain the calculation using the exchange and breaking processes we detailed, focusing totally on color and magnitude and ignoring the decimal point until the final notation.
That's the key.
So after the student has internalized the physical necessity of these operations, phase three builds the crucial bridge to abstraction. This is where we transition that concrete action into an abstract symbolic representation.
This is the make-or-break phase. This is where students transition from needing the concrete material to internalizing the abstract algorithm. And crucially, the physical materials are removed entirely.
So how do they continue the process without the blocks while still maintaining that conceptual link?
They use visual and color coding. The student works on grid paper and they have to use colored pencils. They represent the nature of the digits using blue column for the tenths, a gray column for the hundredths, and they schematically draw the exchanges that they previously performed with the blocks.
Okay, so if they're doing 0.6 plus 0.5, they would write 6 blues and 5 blues. But instead of physically exchanging 10 blocks, they actually draw the exchange.
Precisely. They use symbolic drawing that mimics the material action. They might draw a circle around 10 of the blue units, cross them out, and then draw an arrow that leads to one green unit box, symbolizing that exchange. They're literally mapping the physical action onto the paper. I cross out one blue, and I draw 10 small grays.
So they're essentially using the color as the persistent semiotic code, the visual language, that reminds them of the nature of the quantity, even though the quantity itself is now just a symbol.
It is the perfect conceptual transition. They are still focusing on the nature of the quantities by using color, but they are now solely using symbols and spatial representation. And this forces their working memory to internalize the structural logic of the material manipulation.
And that's how the reliance on the physical blocks fades, but the conceptual logic remains.
Exactly.
And finally, phase four, return to the sementized algorithm.
This is the point where the traditional, efficient vertical algorithm is finally introduced. But critically, it is not presented as the primary instruction. It is presented as an ergonomic consequence of grouping quantities by nature.
It's just the grown-up, fast way to organize the color boxes.
That's exactly it. The traditional column-based algorithm is introduced at the very end of the sequence as the most efficient, practical way to organize the calculation. By this point, the student understands with absolute certainty why they align the columns, because they're combining same-natured quantities.
And why they carry the one? Because they performed a value-conserving exchange.
Yes. The procedure now serves the concept instead of obscuring it, and this ensures the student never defaults back to that dangerous natural number bias.
So we've navigated the architectural flaws of decimal number teaching and explored the systematic solution proposed by this colored rectangles method. It's a really compelling case for pedagogical engineering that creates understanding through constructive constraints. Let's just recap the three fundamental benefits we uncovered.
Okay. First, it systematically deconstructs that debilitating natural number bias by making orders of magnitude physically manifest. This ensures that any flawed comparisons that are based on integer logic are directly contradicted by irrefutable sensory evidence, the mass, the area, and the color of the units.
Second, it provides concrete physical meaning to the seemingly arbitrary algorithms of regrouping, the necessity of exchange and borrowing, the necessity of breaking. These rules are transformed from magical procedures into transparent material necessities, and they're driven by the fundamental structure and constraints of the base 10 system.
And third, it serves as a powerful structural tool for equity. It fundamentally alleviates the cognitive load for struggling students through that strong semiotic coding, the consistent color system, and the externalization of working memory. It reinforces their autonomy and their confidence in mathematical reasoning by giving them time to process.
The systemic adoption of a method like this, according to our source material, really has to be viewed not just as a technical or an educational preference, but as an urgent ethical and educational policy imperative. It aims to dismantle a century-old cycle of academic failure by fixing the curriculum, not by blaming the student.
And the ultimate achievement here is restoring the pact of trust between the student and mathematics. They realize that the algorithm is a logical tool of thought, rather than an arbitrary rule that replaces logical thought.
So, here is our provocative thought for you, the listener, to mull over long after we sign off. If fundamental and conceptually difficult concepts like regrouping and borrowing can be demystified and anchored in material, physical necessity, how many other foundational concepts across your entire education, in complex systems, in the physical sciences, in language acquisition, are currently obscured by syntactic rules and rote memorization?
And what would happen if those concepts, too, were anchored in undeniable physical magnitude or logical material necessity?
It raises the profound question of whether education, at its deepest level, should be about teaching students to follow instructions, or teaching them to understand the underlying logical architecture of the world they inhabit.
Something to think about.
Thank you for joining us for the deep dive.